Academies of Sciences recently launched a strategic priority research program named Advanced Fission Energy Program. This was done in January of 2011 to confront two grand challenges in the nuclear energy world: long-term nuclear fuel supply and permanent disposal of spent nuclear fuel. Today we're very happy to have Professor Kun Chen come talk to us about one of the approaches to these two grand challenges, which is the TMSR program, the Thorium Molten Salt Reactor program, which is being developed at the Shanghai Institute of Applied Physics. Dr. Chen got his bachelor degree in physics from the University of Science and Technology of China in 2001, and his PhD in nuclear physics from Indiana University at Bloomington in 2006. After that, he worked in Argonne National Laboratory as a nuclear engineer until 2011. Since then, he has recently joined the Shanghai Institute of Applied Physics, Chinese Academy of Sciences, to lead the safety analysis and licensing effort as a professor in the institute. Before we get started, just want to lay a couple ground rules out there. This is a technical talk. I notice many people have video cameras and recording devices. Dr. Chen has asked that if you would like to use it for your personal use, that is fine. If you would like to put it and post it online and make it publicly available, please send email to Dr. Chen to get written consent. Second, he's going to give his talk first, and questions will be asked after his talk, so he'll talk for about 45 minutes, and then there'll be a Q&A session afterwards. If you have points of clarification about technical details, by all means, go ahead and ask, but we would like to give him an opportunity to finish his slide package. And finally, everyone's come here to hear Dr. Chen and not yourself. So if you have a question, please keep it to a question and not a comment. We have a lot of questions, a lot of interest from the community, so we want to get as many people a chance to actually respond and have a bit of a back and forth. So having said that, please welcome Dr. Chen.
Well, does this work? Okay. Thank you for the introduction, Ed, and thank you for having me here. Today I'm going to talk about the thorium-fueled molten salt reactor research project in China. My talk has 3 parts. The first part, I'm going to do a little bit introduction on the project that is going on in China. And the second one, I'm going to talk about the history of our institute on thorium molten salt nuclear research. And the last part of the talk is going to be on the 2 megawatt molten salt cooled research reactor design. So I'm going to start with the nuclear power in China. It's not up to date, so it's updated every few months, but my data is not up to date. You probably know better than me on this. So by the end of 2009, there's 11 power reactors in operation in China. There are going to be more reactors in the future. So some estimate that by 2020, there are going to be 70 gigawatts in operation and 30 gigawatts under construction. And that you notice that this data are before the Fukushima accident. So after that, it's going to be slowed down a little bit. I'm not sure how this number is going to look like by 2020, but there's speculations on 2030 that 10% of the electricity in China is going to be from nuclear power. So there's going to be a lot of nuclear power reactors being built. There are some challenges for nuclear energy, as you all well know. There are a few supply issues. This may not be a problem for a country like United States, but for China, there's limited uranium resources. The same thing happened to India too. So if China is building a lot of nuclear reactors, the price for the uranium is going to be higher than what we currently have. There are also challenges on nuclear proliferation because the LWRs produce plutonium. And there are also challenges on nuclear waste, which is one of the major reasons that the nuclear energies are protested in the world. So we were hoping the thorium energy can solve some of the problems to some degree, because we believe that thorium is more abundant than uranium, at least in China's case. There are theory that the thorium fuel, which is through irradiation, will contain uranium-232 that makes the weapon material be impossible. So that may be proliferation resistant. There's also calculations done saying that the more than 90% of the long-term radiotoxicity can be reduced by using thorium fuel, but those are all calculations. So. But there's some challenges on thorium fuel cycles. First, it's relatively difficult to fabricate thorium fuel, especially fuel pellet, compared to uranium. And there's also a longer cooling time for irradiated thorium fuel to breed, because the decay of protactinium-233 to uranium-233, and also the breeding rate for in the thermal reactor for thorium is lower than the uranium-238 in the fast reactor. There are also hard gamma rays from U-232. So those are some challenges on using the thorium energy. And we think that the molten salt reactor may be the solution. Here is a picture of from the Oak Ridge National Laboratory. There are well-known MSRE experiment in the 1960s. So we think that by using the molten salt, the liquid salt, with the online reprocessing, we might be able to solve some of those problems that prevent us from using thorium energy. So this is the fuel cycle we proposed in our project. So we think our final goal would be the liquid fuel thorium molten salt reactor with the online reprocessing. So that is the goal we want to achieve in the long term. We also think that by using the fast spectrum, we might be able to burn some actinides in the molten salt reactor to reduce the waste. But there are problems, there are challenges in this fuel cycle. For example, the online reprocessing is very difficult, at least for us. There are also material problems. There are also containment problems. So people, especially regulators, are worried about that, the leak from the liquid fuel reactors. So aware of that, so we have a modified fuel cycle here, which is a molten salt cooled reactor, which actually uses tristle fuel, the same fuel as used in the gas-cooled reactor. So by using tristle fuel, we contains the radioactivities inside the fuel. So the containment can be a less issue. So, but this one will have a once-through fuel cycle. So it's going to be difficult to reprocess triple fuel, but it also prevent the nuclear proliferation at some point. To better use thorium, to better use the fuel, we have to have a high burnout of the fuel because it went through. So we're going to have a pebble fuel circulation system in the reactor. So if we can, if we cannot use a large chunk of thorium, at least we can reduce the consumption of uranium, so that mitigate our problem with the uranium supply. Okay, I think many of you have already known the difference between the molten salt reactor and the molten salt cooled reactor, but I'm just going to repeat this again. So the molten salt reactors, the same as Oak Ridge has designed and run, it uses liquid fuel. The fuel and coolant are all in the, actually the fuel and the coolant are the salt itself. So, but the molten salt cooled reactor, since we are using triple fuel, and the salt is only works as a coolant, not as a fuel. The molten salt reactors have the potential to have a fully closed fuel cycle. However, the online reprocessing is very challenging. And the molten salt cooled reactor has a once-through fuel cycle, even though it can have a high burnout, but it's still a once-through fuel cycle. However, it can have a high temperature and high efficiency. So now, why does high temperature matters? Because we're talking about the carbon neutral cycle. We traditionally were using nuclear reactors for power generation, but now we're thinking that if we use a high temperature reactor, we can use the heat to do some chemical processing. That one of the solutions for the carbon capture is that we can use the heat from the high temperature reactors to capture carbon dioxide, because we can produce hydrogen by using the high temperature reactor. Then if we combine the carbon dioxide and hydrogen, then we can have methanol. This is one of the possible ways to store energy, because people talking about use batteries to store electric power, but the power can also be stored in the liquid fuel. So by doing this, we may be able to have a carbon neutral cycle. So another reason we promote this is because currently almost all the reactors are used to generate electricity, and the utility companies have a lot to say in develop what type of reactor. It's very difficult to convince them move away from light water reactor, because they're already very familiar with, they're happy with, they're comfortable with it. So we are trying to persuade other companies, like petroleum companies to use the high temperature nuclear reactors to do their job. So that's a potential application. And the molten salt cooled reactor is around for years. So we have a UC Berkeley design here, and we also have Oak Ridge design. We have also a small modular design from Oak Ridge National Laboratory too. We also know that the molten salt reactor liquid fuel one also have several designs by, such as Japanese Fuji reactor. There are also MOSAT reactor from Russia and French design too. Okay, so with all the benefit that the molten salt reactor or molten salt cooled reactor can provide, China is now launched a project on thorium molten salt reactor. So it is a Chinese Academy of Sciences project. The short name is TMSR. They have a news release, I guess, last year. Yes, last year. The goal of this project is to build a 2 megawatt molten salt reactor and a 2 megawatt molten salt cooled reactors. So it's going to be 2 research reactors. Those reactors are for R&D purpose. The budget was committed for 5 years, starting from last year. The total budget is $350 million. We also set up a CAS Center, the Chinese Academy of Sciences Center, to consolidate the effort to basically manage the project, because the project is going to be done by different institutes, universities, so we need a center to manage it. Now here's our roadmap. First, we're going to have a 2 megawatt experiment reactor. This 2 megawatts one, we have already got the money, so we're doing the job, we're doing the work. But we also have a plan for 10 megawatts, for 100 megawatts. So we'll be hoping that if we succeed on 2 megawatts, we can move on to reach the power to build a large demonstration reactor. But we're going to have 2 pathways on the development. One is on the molten salt cooled, and the other one is on the traditional molten salt reactor. So those going to be in parallel. But with the molten salt cooled, have the priority because it's we consider it's more technically ready. So when we can have a fully closed fuel cycle, that depends on when we can solve the problem on the online reprocessing. So, and also we're going to use this. We're hoping we can convince some company to use this technology on either electricity generation or the non-electricity applications. So we're working on that. So here is some major R&D work conducted at our institute. We're doing reactor design and code development, including reactor physics code, thermohydraulics code, structure code. We also developed some equipment that is unique to the molten salt reactors or molten salt cooled reactors. We're not going to develop some standard instrument or devices, but some of the equipment are unique. For example, the fuel handling, the fuel circulation device, which is very challenging for our current pebble bed molten salt cooled reactor. And we also doing design and operation on the high temperature molten salt loops, which include salt pumps, valves, salt purification systems, and this will be used by the nuclear reactor, but can also benefit other fields such as solar power. And we're doing radiochemistry research on pyroprocessing of the spent thorium fuel. That is for the liquid salt reactors. And we're also doing some material development, such as alloys. And we also need new high temperature materials, such as silicon carbide composite for to reach the temperature of the reactor to a certain point that we can actually use the heat to produce hydrogen. And we're also working on the safety and the licensing, which I'm generally responsible for that to basically to get a license for the small 2 megawatt reactor to get analysis done and to do some experiments to demonstrate the safety features to the regulators in China. Because it's a Chinese academic science project, so it must involve other institutes underneath Chinese academic sciences. There are about 100 institutes under the academy. There are large institutes like us. We have about 1,000 staff, and there are also small institutes which only have like 30 or 50 people. So this is not again, it is incomplete list because institutes are joining us every year. So we have Shanghai Advanced Research Institute, which is working on the salt pump and heat exchanger helium and gas turbines. We also have a Shanghai Institute of Organic Chemistry, who is responsible for the salt production and purification. And we also have a Changchun Institute of Applied Chemistry, who is working on the thorium-fueled production and purification. And we also have an Institute of Metal Research, which is located in Shenyang, who is expertise on alloy materials, such as N. So here is the expected outcome of our project. So after 5 years, after many money spent, we're supposed to deliver something. And we're going to have a 2 megawatt molten salt cooled research reactor built in 2015 and a liquid salt molten salt reactor built in 2017. So the schedule is tight. There's a lot of work to do here. So we also want to gain the capability to build a larger molten salt reactor based on the experience on the smaller ones. And we also set up a comprehensive test facility, including the thermohydraulics test loops, including the radiochemistry labs for R&D purpose. So we basically want increase our capabilities and equipment by doing this project, so we can do some other research work. Okay, that was the short introduction on the thorium molten salt reactor project in China. There is multiple news releases from the academy talking about the strategy plans, what's the next step. So if you are interested, you can go to their website. Those news releases should still be there. So now I'm going to talk about the history of our Institute on Nuclear Research. That basically I would like to answer the question is why us? So why the academy asked us to do the thorium molten salt reactor project, considering there are 100 institutes in the academy. So our institute was founded in 1959. At one time, it was known as Shanghai Institute of Nuclear Research. We changed the name in, I think, 2005 or sometime. We have more than 1,000 staff and 300 students. We have basically two big projects going on. One is the nuclear energy, the thorium molten salt. Another one is on accelerator side. We have a synchrotron light source, just the one you have here in the Lawrence Berkeley lab, the ALS. So we have a Shanghai synchrotron radiation facility, which is a scientific user facility that everybody can apply the beam time to do the experiment. We have two campuses in Shanghai. One is in Jiading district, which is for the nuclear research, and another one is the Pudong district, which is for the synchrotron light source. So here's a picture of those two campuses. The one on the top is the synchrotron light source. The circumference of this synchrotron is 430 meters, so it's a large facility. And the one on the bottom is our Jiading district for the nuclear research. Some people don't like the idea that to set a radiochemistry or reactor in the campus here because they thought that's it can ruin the the campus. So we have done some early nuclear reactor work back in the 70s. So actually, we had built a zero power cold state molten salt reactor back in 1970s. So at that time, China started to look at the civil nuclear energy use. The first project in China to build a nuclear power plant, which is actually not using the light water reactor. It was for the molten salt reactor. So the plan was to build a molten salt reactor in China to generate electricity. So that was in the 70s, from 1970 to 1972. There was about 500 scientists and engineers working on that. So what they have is a cold state. That means the salt is not molten, so it's a solid salt. Basically, it's a zero power test device. They were able to reach critical and do some neutron experiments. So, but after the container of the core at that time, was made of aluminum. So after a few months, they found that aluminum is heavily damaged by the corrosion. So they evaluate the situation. They think that it's impossible for them to produce a reliable material that can actually, work in the molten salt reactor. So then shifted the effort from molten salt to light water reactor, which is from 1973 to 1975. So at that time, we also built a zero power light water reactor test facility, and eventually that effort leads to the first Chinese power plant, which is Qingshan nuclear power plant. So in some sense, that the civil nuclear research start from our institute in China. So we actually the first institute in China start working on this nuclear power generation. So it's the picture in 1970s, which actually a light water reactor. You can see the guys load a few bundles here. After the experiments done, so our institute actually separated. There are scientists remain in the institute doing some basic researches. There are also engineers that go on to form a company which is focusing on design the PWRs, which still exist in Shanghai today. I think some of you may know their name. They call themselves SNERDY. So they're actually, at that time, they're actually working with Westinghouse on the AP1000. So we're from the same origin, but they they're moved to the more like application part, where we remained in the basic research field. So. Okay, here's a little bit history of our thorium research. So our research on thorium utilization actually began in the middle of 1960s. So in the late 1960s, we were able to separate about 6 G of uranium-233 from irradiated thorium dioxide. We started the thorax processing in China back in 60s. In 1970s, we did some hot experiments in our institute to reprocess thorium fuel. But of course, it's lab scale. In 1980s, we also did some work with Tsinghua University on whether we can reprocess thorium fuel from the high temperature gas-cooled reactor. So, those research continued until late 1990s. We had, in the time between 60s and 90s, we had done some work on irradiated thorium samples in high flux reactor. We have done some critical experiments. We have also studied the possibility of using thorium fuel in PWR. Those works are funded by different agencies, which only a small project. Some of them are funded by IEA at some point, but those are small projects. So, but all the work started in late 90s. So here's a summary of our history on nuclear research. So we start from 1960s. Actually, if you look on the top, those are the reactors we're building at that time. We had a PWR. We're trying to build a 25 megawatt MSR, but the project was canceled due to the material problem. Then we moved to the 300 megawatt PWR, which eventually leads to the Qingshan nuclear power plant. At that time, we have a swimming pool reactor on site. We have isotope reactor on site. Here, at the bottom, we have several lines, which basically are several areas of research we have done at those years. The solid line you saw there is actually nuclear research. So we have zero power reactor design. We have isotope separation. But you can see those two works stopped in 1990s. And we also have a nuclear data team there. They were also doing some tritium and DSM-7 research, but those funding are stopped again in 1990s, so they shift their field to nuclear physics. So we had a radiochemistry team to do the processing, but the money is cut, so they move on to do some nuclear medicine work. They also health physics. We set up the health physics team for the reactors, but eventually they end up doing work for the extra reader. So basically, the money is cut in about 80 or 90s. So people, some people get laid off, and some people move to a new field. And that's also, I think that's also the reason we changed our name from nuclear research to applied physics, because at that time we saw that the nuclear energy is dead. So we're going to change our names so we don't, but we still be proud of what we've been doing. So we keep the letter N there, stand for nuclear. So because we call it Shanghai Institute of Applied Physics, so we should call ourselves SIAP, but we keep the N there to show people that we've been doing nuclear research. So what we have done in the past 10 years since we stopped nuclear energy work, we've been working on the accelerators. We've been building the Shanghai synchrotron radiation facility. I'm going to talk about this a little bit. It's a series of accelerators. It has a 150 MeV linear accelerator, which accelerates electrons. Then the electron is injected to a booster, which will be accelerated to 3.5 GeV. Then from the booster, the electrons go to the storage ring, which is even bigger. But when the electrons change their directions or oscillate, they will emit the X-ray. The frequency of the X-ray depends on the energy, the acceleration of the electron. So when they have the X-rays, they're able to build a scientific facility to use this X-ray. There are supposed to be 50 beamlines there. Most of those are biologists. They're doing some protein DNA work on that. They're also material scientists. They're also pharmaceutical companies doing research work there. So they do have their own plans. So we have two campers doing different things. Our nuclear guys have our goals to build big, large reactors. They have their own plans. So they're going to fill all the white space there with beamlines to experiment. They're also looking at the opportunities on the free electron laser beam, which is the same facility as the one in Stanford. So, okay, that was a little bit history of our institute. Now I'm going to introduce some of the design details of our 2 MW molten salt cooled reactors, because that is a major deliverables for our project. So why build the 2 MW research reactor? So what is the purpose for that? So we would like to gain some experiments on design, construction, and operation. Because the last time we were building reactors was in the 70s, so we kind of lost the capabilities somehow. We have some retirees. We want to hire them back, but so there are only few of them around. We also want to test the equipment and safety features that in our design. So that's the reason we don't want to go directly to the large size commercial reactor, because we think we're not ready to design and fabricate those equipment. We like to do more tests on the smaller one. And we also want to validate our models and analysis and codes on this smaller reactor. We also want to accumulate operation data for large size reactor design and licensing. So we want to accumulate enough data to convince our regulators that the molten salt cooled reactors are safe. Here's the basic design or parameters for our 2 MW reactor. We're going to use a triple fuel and 6 centimeter diameter fuel pebbles, because that's the fuel we can readily have at this point, because this fuel is used in Tsinghua University's high temperature gas cooled reactor. We have a goal to build a reactor in 2015, so we have to use some available fuel rather than develop our own. So then we have moderators because the thermal spectrum reactor, we're going to use light salt with enriched TMSR. The temperature we're going to run the reactor is between 600 and 650, and there's argument within ourselves that what is the ideal temperature. Of course, we like to have a high temperature to prove the high efficiency, but there's a limitation on the material that how high we can go. So currently, we think 600 to 650 is acceptable in terms of safety. The core dimension is going to be 1.3 meter by 1.3 meters cylindrical. So it's a relatively large core considering the power of the reactor. So the power density is low. So this is a few of this reactor. We're basically using the same pebble fuel as the Tsinghua University is using in their high temperature gas reactor. So it's pretty much standard. And here is the first version of the design of the core, which is in preliminary stage. So many things are going to be changed. So the red zone represents the pebble fuel, and the central zone is currently, we have different options. We are thinking about just putting fuel there, or we can put thorium there. We can also put some channels there to do some measurements. And the control rod is going to be around the fuel zone. So. And this is a big picture of this 2 megawatt reactor. Again, it's preliminary, which will have a fuel pebbles circulation system. We'll have a decay heat remove system, which will be a pool type design. So you will find that many of the features may not be necessary for a small 2 megawatt reactor, but we like to put more features there to test it. So because the tested reactor, so we'll want to do some tests on it. So some of the features may not be necessary just for test purpose. So here is some parameters. So there's the number of fuel pebbles. It's going to be around 10,000. I guess let's see which one is. So the power density here is very low. So there are just advantages using a low power density here because we're talking about that molten salt cooled reactor can have high efficiency. So we need to show people it can reach high power density. But since it's our first test reactor, so we want to keep the power density lower, but maybe not that low. So it's just the we have people working on different areas. So the reactor physics people, they want to keep this low, so they're more confident on that. But the material guys, the chemistry guys, they want raise the power to do more experiments. So we're still working on that. Okay, there are some safety features for our 2 megawatt reactor. So those are the features. Most of the features apply to a large size reactor, but some of the features may not apply to a larger one. So we have a tristle field here, which can sustain high temperature. We have a low power density here, so the when the accident happened, the temperature may not rise very quick. We have the option to raise the power in the future, but for this moment, we think we keep the power low. We have a poor type design which mitigates the loss of coolant. We have molten salt coolant that has large heat capacity and good thermal conductivity, so which keeps the temperature variations small. We also the salt also has a high boiling point, so we can use a system that operates at low pressure. And again, the coolant salt may trap fission product and actinize in the accents. So, and also the coolant freezes about 400 C. So that's a disadvantageous at some point because you have to heat the pipes to heat the containers. But it also has some benefits to us because when you have accent, the coolant leak, if the coolant leaks from the container, it may become solid, so it won't spread around. There are also relatively large negative temperature coefficient. So based on the current design, we have -9, but it will change if we change the design a little bit. And there are some challenges for our development. The most important one is material. So what type of structure material we are going to use if we want to raise the temperature, so what type of material we should be using. And also we have challenges on the fuel pebble handling devices. And okay, 2 minutes, right? Okay. Okay. And also the production and purification of the salt. Also the reactor licensing, because the regulators in China are not familiar with molten salt reactor. They are more familiar with PWRs, so we have spent some time to educate them at some point. Here's the schedule of the development. So we need to have a pre-conceptual design in June this year. Actually, we have done that. It has been internationally reviewed in July. Some of the people from Berkeley actually went there to review our design. We have a technical design due next year. So construction needs to start in 2014, and the reactor is scheduled to go critical at the end of 2015. So of course, based on the development schedule, we also have a licensing schedule here. So I was talking about the molten salt cooled reactor. In parallel, we're also developing a 2 megawatt liquid fuel molten salt reactor. Here is some basic parameters, and we're not going to have a reprocessing for the 2 megawatt one. So in summary, the Chinese Academy of Sciences has launched a thorium molten salt reactor project in 2011, last year. The TMSR Center in Shanghai Institute of Applied Physics, which I worked in, is leading the effort. And there are two megawatts reactors will be built between the year of 2015 and 2017. So with that, I'll take any questions. Yes.
I have two questions. One is, I'm curious about beyond the 2 megawatt reactor, how long it would take to go commercial. Even for a 2 megawatt reactor, that was one of my questions. In the abstract, it was 2035 or 2030, and I'm wondering why you have, in the abstract, you have 20 years between the success of this R&D reactor on the one hand and actually commercializing it on the other hand. That was the first question. The second question is it was a little unclear to me because you're doing 2 different reactors. They're really quite different.
Yeah.
But on the MSR version, what are the thoughts about using one train of fuel mixed in, or titanium mixed in with the fuel, or separating it out until it decays into uranium-233? What are the thoughts on that? This is a debate in the United States on the same question. Which is the best way to go?
Okay. For the first question, because our plan is to build a 2 megawatt first, then we're going to build a 10, 20, or 30 megawatts reactor. Then we go to 100 megawatt or 200. So we have to do that step by step. So to build several reactors before we actually build a large size one. So that would take us like 20 or 30 years. And also, well, those 2035, 2040 are only the years we put in our proposal. So it's not a fixed schedule when we're going to commercialize it. It's just our, yes. And for the second question, for the molten salt cooled reactor pebble bed one, we're thinking that we put several thorium pebbles inside and doing some experiments. So basically to get some data, not seriously produce any uranium-233, maybe in the future, but not for the 2 megawatt one. And for the liquid-fueled molten salt reactor, we're seriously thinking doing the conversion from thorium to uranium-233. So yes, there are two ways to do that. You can just remove the fuel from the core that sit there for like 30 or 60 days. So we're also evaluating that. There's no, we haven't made our mind which way to go. Yes.
So 2015 for criticality for the molten salt cooled reactor.
Yeah.
Is a very aggressive timeline.
That's correct.
You mentioned very briefly a number of the technical challenges that need to be met in the time period. What do you do as kind of the biggest challenges or obstacles to overcome to meet that aggressive timeline?
You were asking which one is the...
What are the top priorities, the biggest concerns in order to meet that aggressive timeline?
The biggest concern is of course the material. So
Is that the vessel material, the heat exchangers?
both material. Yes.
My understanding that you're going to be using lithium-7 enriched salt.
Yes.
Salt. Are you working on facilities to produce that? To my understanding, there are no facilities in the world to produce the lithium-7.
There's some facilities in China that produce it. It's not a very large-scale facility. It doesn't produce a lot, but we're persuading them to increase their production. So we'll see where it goes. So, and those enriched lithium-7 are not highly enriched. It's probably only 99.95. So.
further enrichment than that, or are you planning on just living with that?
It's ideal to have a high enriched lithium-7,
Yes.
but it does not depend on us. It's depend on the company, so how much money we can pay them. So.
Is it a mercury process?
I'm sorry?
Is it the mercury process? Or?
Yes. They also have new techniques, but it's in lab scale. Yes.
What kind of fissile material do you expect to start up these molten salt reactors? The 2 megawatt and then the
Uranium 235.
And is that, what's the enrichment you would expect?
10%.
Is that true for both the cooled and the fueled reactor, or just the cooled one?
Just the cool one.
What are you planning to use for the fueled one?
That we haven't decided. Yes.
Are you collaborating with any of the other countries that have done this sort of molten salt, like France and Japan and Russia?
We talked with them at some point. We also talked to Russians, and we're still working on how to work with them. So there's no real steps there, but it will be some real collaboration maybe next year. So yes.
Well, if you need an U-233 to start up the molten salt reactor, we have some. Pump DOE friends.
Well, that's good to know.
But we're planning to waste $500 million on destroying it, so you might want to talk to them before they get that contractor wasting more of our taxpayer dollars. What is the relationship of your Tsinghua HTR pebble reactor to the German one? I thought that was given to China some years back.
Yes, that was what I heard. I was not involved in the high temperature reactor project, so I don't know exactly what's the relationship, but that's what I heard was, I think the same as you said. So. Yes.
Have you selected a designer? Is there one person who is the designer for the 2 megawatt molten salt reactor, the traditional molten salt reactor, or is it a team that's working on it?
It's a team. Yes.
On the turbine, what crushed the South African PBMR was the R&D that went into trying to develop a closed cycle gas reactor, Brayton cycle reactor. Who's doing that research? Is that part of your institute, or?
No, it's not a part of our institute. It's part of the Academy of Sciences. It's a different institute. They're located in Shanghai. They're actually developing that for coal-powered reactor. Yes, the power plant. Yes. Yes.
What salt were you using for your intermediate loop?
Flyneck.
Flyneck, and is it the same for the buffer salt?
Yes, that's right. Yes. You mean the molten salt cooled reactor?
No, in the pebble.
In the pebble reactor, yeah.
Where will you be getting the thorium?
We have institute that is able to make a few, several thorium pebble fuel in their lab. So we're not sure about the quality of the fuel, but they are able to make several. So we can at least do some experiment. We were talking with the manufacturer. We produce the regular pebble fuel for Tsinghua University, and they have some difficulties working on thorium. So.
And what scale are they working on?
You mean for the regular pebble fuel?
For the uranium?
But you mean that large scale? That's for I think it's for a 200 megawatts demonstration gas cooled reactor. So it's large scale. Compared to them, our 2 megawatts only use a few of their pebbles. So.
think we have time for one more question, and if you're able to hang around a little bit after.
Yeah.
People want to ask some more questions afterwards. So
Yes.
I'm curious about the structure of the project from a funding perspective. About $70 million a year. I assume that the spend is more or less flat over the 5-year project?
We spend the money based on the budget that we propose. So when we write the proposal, we have a plan to spend a certain amount of money for each year.
So that works out to roughly 1,000 people involved. $70 million a year buys about 1,000 technical people.
In our institutes, there are currently about 300 people working full-time on it. There are about another 100 people from our outside to work on it. So a total about 400 people working on that.
Is that calculated based on just converting the yuan to dollars? That's where you come out with 350 million?
Yes, that's US dollars. That's converted.
Just a conversion.
Yeah.
And that buys more in China than it would here, I suppose.
Not necessarily. No, because the tax is high. Because you have to pay the tax. So.
All right, why don't we go ahead and thank our